Welcome everyone to part 10 of the ESTeem wireless training class. What we're going to concentrate today is actually on the last series of radios that we're going to cover, which is our 210 series of radios. Much like that we covered in our last session, these radios actually function on the license frequency bands that do require that you have a FCC license to operate within those frequencies. And let me give you an idea of what I'm making reference to here. What these series does is that these are really the higher speed, really built for more Ethernet based applications that fall within the license frequency bands. What I'm making reference to here is that generally these license frequency bands allow us to go to much higher output power within the radio itself. Those higher output powers then translate really well towards longer range type applications. You also get the benefit of having an FCC license frequency, which means that you essentially have a lease for that frequency within the geographical area, so that if anybody does cause interference to your operation, you have a legal recourse to get them off of there. These radios support both serial and Ethernet interfaces, but these are primarily, if we're going into the license frequency bands of the 150 megahertz or the 450 megahertz frequency bands, these are the ones that we would typically use for the Ethernet transactions. Again, these maximum throughput on these radios is about 65 kilobits per second, so it's not something that you're going to use for high-speed networking. You're not going to use it for cameras. You can do a limited remote programming through the systems, but overall they are primarily built for data collection. Both the VHF and UHF comply with the 2013 narrowband mandate, and so these have actually always been narrowband compatible. Looking at how the 210 is actually laid out, going kind of from the left to the right here, unlike that we saw on our other radios, this one actually has 4 different LEDs, and each one of them indicate a different aspect of what the radio can do. For example, the power LED, that just designates that the radio is receiving power. It does not tell us whether it's good power, clean power, the correct voltage. It just will illuminate if we are receiving some type of power into the radio. So we don't want to use that as any type of diagnostic. The next one is the receive LED. Now, the receive LED on the 210 is actually, best think of it as actually a carrier detect. This receive light will go on anytime that anything is on the operating frequency that radio is configured for. That is enough to trip the carrier detect. So it doesn't necessarily mean it's another ESTeem in the system, but it is something that is operating on that frequency. The next one is the transmit LED, which I have a little label down here. That transmit LED is pretty self-explanatory. The only time that is actually going to illuminate is when that radio is actually sending information over the radio link. The status LED will illuminate as soon as this radio makes a connection with another 210 radio in the network. If there are 4 different radios that it communicates to, really the status LED will stay illuminated as long as it's got one of the 4. It's very quick identification. It doesn't give you much more detail than that. The 210 series is a little bit unique in our radios in the fact that it actually has a receive signal strength indicator on the front. Again, going from the left to right, the next button you're going to see is actually the reset switch. Now, the reset switch functions much the same way as plugging and unplugging the power going into the radio. There's nothing you can do to it as far as resetting the radio to factory defaults or anything like that. The only thing that reset does, it's just refreshing the radio's configuration as if it were new. The 12 volt DC input next to that is actually it's a posi lock connector. So the nice part is that there is no way to invert the connection into the power. It can actually only be put in one direction. So what we have is we have a power supply or the radios themselves actually come with the mating connector of that, so that you can put in there the positive, negative, and ground into those 3 ports. This radio does support 10, 100, and 1 gigabit as far as the speed into the Ethernet port. Unlike any of our other radios, for a backup communication, instead of having a serial port, an RS-232 serial port, this one here we actually built with a USB programming port. There is a series of drivers to make the USB programming port appear as a normal terminal. And to do that, just as simply as you download those from our website, it's going to come up and look like any other communications port on your computer. This one also has an RS-232 data port. So unlike all of our other radios, instead of having it in an RJ45 or an Ethernet-based looking interface, this one has a standard 9-pin port on it. Looks like the port on a computer. So some of the particulars for each of the radios. We actually have 2 different models within this 210 series. The VHF version of this is the 210M. It covers the frequency band 150 to 174 megahertz. Really the biggest difference between this and our other generation with a 195M is the fact that this one actually uses a much more dense modulation technique called QAM, QAM. And we'll get into exactly what that modulation looks like. That very high-end modulation level, because we can actually go up to 64 QAM within these radios and still operate within a 12.5 kilohertz wide channel, which technically is incredibly difficult to do. Because of that channel density, we can actually get 64.8 kilobits per second on a 12.5 kilohertz wide channel. So of the narrowband radios out there, this one is the fastest on the market. Now what we do is we actually put in there an average power level at 2 watts. The radio itself can actually go anywhere between a very low output power all the way up to 10 watts of output power. Where that comes from, though, is unlike any of the other narrowband radios that we deal with in the licensed channels, this one doesn't come up and put up a single carrier output and then modulate the data onto it. The data is actually modulated within the actual carrier stream. And because it is a quadrature amplitude modulation, the power level is actually going to change on each data block. This may seem a little confusing, but once we get some of the graphics up here, it'll make a little bit more sense. So the power level that we have listed here is actually just as an average of 2 watts. The radio actually itself can actually transmit up to 10 watts if necessary. What that really correlates to is about a 10 to 15 mile line of sight range. Now we actually have multiple modes of operation within these radio, and we actually have 2 different generations of firmware that go within these radios also, depending upon the type of application that's going to be put into. The first generation actually supported Ethernet bridge mode. In other words, the data would come into one radio and that data gets rebroadcast out to the other remotes. And the way that we limited the amount of traffic going between those is we have generally in most of those, the remote end is in what we call a bridge mode, a station bridge mode for mobile applications. So you'd actually have a one master as an access point, and then the station bridges would connect into that. The idea behind this is because we still only have about 65 kilobits per second, we want to give all or as much of that data as we possibly can give it to the actual throughput of the connected devices. The radios themselves actually do work with a mesh technology, but with a mesh technology and the bridge mode, we found that the actual beacons and everything that's required to maintain that bridge ends up utilizing about 1/3 of the actual RF data rate. So in most cases, we try to limit the amount of traffic we possibly can put into it. That's what really pushed us into the second generation of firmware, where we put in what we call a router mode. And a router mode, really what it does is it locks down the communication, only allowing communication to go across to the remotes that are specifically for those devices at the remote. It does take a little bit more programming within the radios, but at that point you can lock it down specifically to that traffic. Another feature that firmware enabled was we actually put within there what we call an Ethernet IP proxy. Part of the Rockwell's Ethernet IP protocol uses something called a keep alive packet. Well, those keep alive packets are used to maintain the link in their Ethernet communication. Well, we are already maintaining that within the radio. So what we do is if we see that request for that particular type of packet stream, we can answer that locally, or we can proxy that answer within the local radio. That gives you a tremendous amount more throughput on the system. So if you've got a network that is looking to push through as much data as it possibly can, in most cases it ends up being within the router mode. The radio can support high-level 128-bit AES. That is going to be standard, and even the lower actual throughput security measures like TKIP, which was really for the first generation of WPA. But because this is not a Wi-Fi device, we don't want to use those type of terminology, or it'd be a little bit too confusing. We also have the ability to use the access control list. So if you are using these in a mobile environment, to where you're actually having the mobile stations link into multiple access points, you can configure it so that either the client will only speak to specific access points, or you can configure it from the access points and only limit the particular clients that it goes into. Those are really some detailed application notes that we can get to. Most of those actually come in from the public safety side, where we've used these for fire, police, EMS. As an alternative to the 210M is actually the 210C. Now, as you see here, the only difference really between those two radios is the frequency of operation. All of the other parameters as far as power, distance, modes of operation, security, everything else is the same between those two radios. The only thing that's any different between it is actually the frequency of operation. Now, what really sets these apart is these are what's in what's called a licensed frequency band. Now, in all honesty, there is no such thing as an unlicensed radio. The only difference is who's required to get the licensing for the hardware. Now, because this is can be set to a specific channel, and that channel is actually authorized by the FCC, this one actually will be directly given out by the coordinator and the FCC. It's really an FCC license is actually two parts. There's one that actually goes to the government entity of the Federal Communications Commission. Well, the Federal Communications Commission themselves do not actually license or coordinate the individual frequencies within an area. That's actually done by a secondary firm that is essentially works for the government, which are called coordinators. And there are different coordinators depending upon the type of license it's going into, whether it's an individual business, forestry, oil and gas, public safety. Each of these have different coordinators. So the cost and filing time really depend upon the coordination fees. Because there is so much that goes into the back end of this, though, we usually recommend going through what's called a licensing assistance office. And really what they are is they are a company that puts together all the paperwork for not only the FCC, but the coordinator. The nice part is that because it is going through essentially a licensed agency, as soon as it comes back out of the coordinator, you can actually operate on that frequency, even though it can take up to 6 months to get the FCC license itself back from the government. But you can actually operate on this in-term license really as fast as 4 to 6 weeks. The idea behind this is, though, it's not basically a government overreach trying to figure out what's happening in an individual area. It's really bringing order to what could be essentially a chaotic situation. If everybody out there got to choose their own frequency and operate on any channel at any power they wanted to, the one that put out the highest frequency at the widest bandwidth would always win. So what this frequency licensing does is it gives the ability to everybody plays on a level playing field. And if somebody comes up and bothers your operating system, you now have legal recourse to get them off. Another thing about licensing, it has actually changed to a 10-year license. So what you're actually getting then is, even though you're going to front end pay the licensing assistance office, the coordinator, and the FCC, generally most of the licenses are anywhere between $600 and $1,100. and that is good for 10 years. So if you look at that over the 10-year lifespan, it's really not that great of an imposition. These radios support both Ethernet and serial interfaces at the same time. Much in the same way that our Horizon series operated, we are actually packetizing the serial data packets inside of the Ethernet packets. So because of that, we can actually run both the Ethernet and the serial interface simultaneously. Where that becomes important is if you're looking at upgrading a control system that currently is operating on serial but is looking to the future to go into Ethernet, we can actually support that with one single wireless network. The same wireless network can be operating on serial today and then gradually move each one of the remotes into Ethernet as each of those sites gets updated. The beautiful part of that is because the serial data is such a fraction of the amount of traffic going across there, the serial data has very little impact on the bandwidth overall. And this serial over Ethernet, really what it does is that it's a little bit unique in the fact that we do have an actual serial port within the radio itself. The serial data is actually transferred over the Ethernet system, so the configuration of a serial-based network is identical to that of an Ethernet network. The serial links in this system are transparent. There are no emulation drivers. On our previous training class, we went into exactly what the emulation drivers allow us to do. For this type of a network, there really are no transparent. And almost just about any control protocol in the world will actually work over a transparent connection. The only one that does not function that way is Rockwell's DF1 full duplex protocol. It does require having a radio that has an emulation driver, like our Model 195 series. There are two ways to send serial over Ethernet. We can either send it to point. Either you're going to direct that traffic to one single remote site, or you're going to transmit it to everybody. So with one of those two configurations, we can actually work both serial and Ethernet. So if we take a look how come these actually go significantly slower? Quite honestly, it's all a matter of bandwidth. For example, if we were to look at this in comparison to size, a 20 megahertz wide bandwidth, which is comparable in what you'd get on a Wi-Fi network, to give you an idea of the amount of bandwidth we're pushing through here is actually 12.5 kilohertz. So it is a significant fraction of what's available to it. And bandwidth works just like the width on a pipe, a water pipe. The greater the bandwidth, the greater the width of the pipe will allow us to actually push through a tremendous amount more data. So that bandwidth allows us then, if we look at that as far as data rate goes, so a 20 megahertz wide channel can go 54, 72 megabits anywhere in that type of network, in that kind of neighborhood. So the actual throughput that we're getting at the 12.5, it gets us 64.8 is the maximum we can do. So the bandwidth directly controls the data rate. We're at a limited bandwidth. That's really how come the maximum we can do here is 64.8 kilobits per second. Well, if you compare that value to the same bandwidth that we do on a direct, our direct series for the serial radios, those actually operate at 12.5 kilobits per second. So how do we get so much more speed out of these radios than we do out of our other series? These radios actually use a much more upscaled modulation called QAM, or quadrature amplitude modulation. Really, the best way to conceive this is if you were to look at a flat plane, really what this does is instead of operating the signal on looking at changes within, say, a frequency shift, what you actually can do now is that you're actually putting two carrier waves set off by 90 degrees. So each of those will allow modulation between it. Because we are actually pushing it into multiple quadrants, you actually can use what are called symbols. So instead of making just a straight 0 or 1 based upon a high or low, we now have the ability to put in, say, a 0, 1 or a 1, 1, 0, 1, or up to a 16 level to where it would be 4 digits. So each one of these allowed us to put more and more data into a smaller space. The difference here, though, is quite honestly what's called a constellation that it makes. That really affects the output power of the radio. So that is what is unique about this, is the fact that the output or the type of data packet that the radio sends out actually controls the actual output of the radio. Now there are three different types of modulation that we support, either 4 QAM, 16 QAM, or 64 QAM. And that really comes down to how many data points do we have within this constellation. So the higher the order of constellation, the more bits per second we're going to be able to push. The only thing that is more difficult is that the more dense these constellations become, the more subject they are to interference. What we found as kind of a general rule is to actually get 64 QAM, the highest level, you'll generally need a direct line of sight. If you don't have a line of sight, you're either going to be running 4 or 16 level QAM. So what those end up being is 43 kilobits per second or 20 kilobits per second. So the only difference is that it definitely can do this. It's just more affected by RF noise and multipathing. So let's take a look at actually what's making sense here. So where normally, if you were to look at a kind of a side-by-side path to where we were talking about a normal frequency shift key, what you'd be looking at is a sinusoidal wave that would change frequency based upon the data that it gets here. Now you'll have to bear with my little rough diagram here, but really what this would do is say this would represent a 0, and the change in here would say represent a 1. Now our other radios, our 195 narrowband radios, they actually have what's called a 4-level FSK. So I'm going to write it out here on the side. So what you would normally have is a single plane, but what it would do is, depending upon how close these waves are to each other, will represent basically a 0, a 0, 1, a 1, 1, a 0, 0, or a 1, 0, based upon the width that they have there, which is called a 4-level FSK. Why this becomes important is we're thinking of everything in essentially one plane. Now, what we're actually doing is, by using a QAM modulation or quadrature amplitude modulation, we're now where we would basically take this and basically rise and fall signal. What we're actually doing is we're kind of looking at the end point of this. So if we were to look at it on a single plane, it effectively would modulate on one single area. So what we're doing is that we're actually doing this in 2 phases. So that is one phase here, and the second phase here is represented by the secondary line. So what you're doing is, if possible, you're kind of looking, if you would say that, down at the end point of this as if it were coming at you. Okay. Now, what we're now doing is coming off this center point here, and we're pushing that signal out to these various constellation points. So what it allows us to do is, in a 16 QAM modulation here, as you see here, we have 1, 2, 3 points per constellation. Or if we were to talk about this as a 4-level QAM, there would only be 1 point in each one of these axes. So then the transmitter can actually push between like I mentioned to you, 1, 0, 0, 0, 0, 1, and 1, 1, depending upon the constellation point. So as you can see, this wave is actually going to be transmitting to all these individual points as it's coming to, if we're looking at the endpoint, kind of coming to us in over time. So let's go ahead and compare that really to a 64 QAM constellation. In a 64 QAM constellation, you can see there are actually 16 points of reference within each constellation. And again, what we're talking about is 2 phases here. 16 points within each one of these. So now you can easily see, depending upon the type of data, if we have one symbol, that symbol actually represents this one, this one, this one, and this one, all at the same time. The constellation actually represents it. That could actually push the power towards 10 watts. So depending upon the type of data that the radio is transmitting or modulating is going to greatly affect its output power. That's why it's very difficult to say, what is the output power of this radio? If we're to look at this on a spectrum analyzer, what we're actually looking at, as you can see here, this is a 12.5 kilohertz wide channel that we're representing here. So this one actually comes up, and as you can see here, it kind of creates this plateau across the top. That's the radio utilizing all the available bandwidth to it. And to give you an idea of what the 64 QAM modulation looks like in operation, as you can see, that signal is being fired out and this is multiple transmissions all at the same time, but what it's doing is each one of those yellow dots, that's actually an end point for the given signals. So as you can see here, this is a very complex method of modulation, but it allows us to put tremendous amount more data into a small, very narrow bandwidth. Now, when I mentioned to you before, there are actually two different generations of firmware available to the radio, and that really dictates which modes of operation that radio actually has. The first generation of firmware had both an access point bridge that had talked to other access point bridge, just like in the way that the Horizon series did. So you'd create those as a peer link to each other. The only downfall to creating a link between an access point bridge is that those two need to be in constant communication by what are called beacons. They need to make sure that the other radio is there, if it's receiving the data, what kind of signal it's picking up, if there's any changes into its networking type. All of these need to be in constant communication. So there is a tremendous amount of overhead that's associated with that. Now, in most of those networks, we generally had a limited number of those. So the access point bridge would be used at your base and your repeater, but the remote points would actually be in a mobile, or what we call a station bridge. The reason that we would do that is the station bridge only connects to an access point bridge, so they wouldn't interlink between the remote sites, but there are no beacons required talking to a station bridge. So we could greatly limit the amount of throughput or the amount of data necessary to send across that network. Because of the different types of networks that we put in, and these radios have been around for quite some time, we actually do have a second generation of firmware, which we call the router mode. What this does is much like the router that we discussed in earlier versions talking about the Horizon series. This will allow the radio to only send across the wireless link those specific IP, either specific IP addresses or groups of addresses that fit within that profile. So you could put this radio, connect it to a very wide network, and only the traffic for those remotes would specifically go out to it. That second generation also supported the bridge, but we had the ability within this radio to turn off the beacons. By doing that, it gets rid of the meshing side or the meshing capability of the radio. But in most cases, because of the overhead that was required in it, it really was not used in this series of radio very often. Both of those actually support, I guess probably the best way to put it there would be like this. They do also support what's called the Ethernet only mode. That's a diagnostic mode within the radio. So what does this AP stand for? Well, the AP stands for access point. The access point is the mode of operation that will allow communication between mobile clients. It's really was developed for essentially Wi-Fi type access, allowed roaming between different environments. It is available in the 210 series in the station bridge, so they can actually roam between multiple access points. The idea here is that the access point allows these mobile clients to communicate with each other also. It acts as the relay point. The idea is to expand the range between the mobile clients themselves. Now, the access point bridge, quite honestly, is one of the most commonly used modes of operation because that's what you really want the data to do. You want the data to transfer everything that it picks up on one side, you want it to be sent out to the remote. The only downfall to that is the fact that in a bridge system, all traffic that radio receives. So if you were to plug it into a business switch, something like this, all the traffic for everybody that goes across there is going to try to push over that wireless network. So what we did is we had to start developing ways to kind of limit the access to that, or try to negotiate or put in different ways of limiting what data goes across there. Now, because it is in a bridge mode, all data is shared. That's really the key here. The beautiful part is that it is a simple configuration. There's only one single IP address required. There is no routing information required in there. You'll usually use this for fixed locations, and the big thing is it's going to be small or isolated Ethernet networks, only those that are talking to themselves. It does create this backend, as I mentioned to you. The mesh portion of the radio can actually function within the system, and it does work perfectly well. The only downfall to that is, again, the mesh ability does require a tremendous amount of overhead. So we found through measurement, it can take easily up to 1/3 of the bandwidth just to do the meshing component. But if that is a priority in the system to where you have redundant routes, the radio can support it. It's just that is the downfall to it, is that you do have to create it. The nice part is that they are self-healing in the fact that there is no maintenance that needs to be put into them to get it to work. The ether stations themselves, it's very simple. What they are is they are in a mobile environment. So the only two things that they're looking for is they are looking for the SSID, which is the name of the network, and the encryption level to be correct. Really, what you're going to use them for on the 210, these are going to be the end nodes. Whether or not there's no repeating, nothing's needed there, that's going to be the end point within the system. So the traffic for it, there are no spanning tree packets required across there, but it will actually then be used essentially at the remote node or in a mobile environment, as we see here within the network. The station bridge mode, the nice part is that there are no, it supports multiple devices. So if you've only got a single remote, you'd still use a station bridge, even if you're even plugging it into a network that had 10 devices connected into it. That same mode works in both of them. Really what it's doing is it's consolidating all this into all these multiple IP addresses into a single device. It does make simple bridge-like configuration even at the remote ends. There is also minimal network management traffic, and it does have the ability to roam. So if you do have essentially multiple access points up, if one were to fail, it would automatically roam over to the other access point until the point to where it came back. Because we're dealing with a bandwidth within these radios of maximum at 65 kilobits per second, when you put this into a larger control network or one that is not really optimized for these slow speed transactions, it would be very easy to overflow the radio as far as its capability of being able to process the traffic. So there were elements that we put in. These are very typical or very standard features that you would find in, say, a managed switch. The first thing is that as part of normal Ethernet radio transaction, there is something that goes out called an address resolution protocol, or an ARP type of packet. What the ARP packet does is it consolidates, or actually gets it gets the MAC address, which is the hardware layer, linked up to the protocol layer, which in most cases is TCP/IP. So if the radio goes out and has information to send, it's going to send it to an IP address. It sends across the network and says what's the device level piece of component that has this IP address. Then it returns a response to it that says, okay, that's my device. Well, most of these are in a very static environment. The only problem is that most ARP packets actually time out in about 3 seconds. So if you're talking about a control system that can take anywhere from 10 to 15 seconds to get to all the remotes, by the time it comes back to the first one, its ARP is timed out, so it would have to send it again. So each one of these is just wasted over-the-air activity that's not necessary. So what we've done is we've added within the radio what's called an address resolution, or a dynamic ARP proxy. What it does is it keeps locally, it says, okay, if I've sent to this address once before, I'm going to keep this information. So instead of sending that ARP request over the air, I'm going to answer it within the radio. So it takes a tremendous amount of the overhead activity off the air and allows it to be done in a local time. The only difficult portion about this is that what you're doing is you're creating an address to a specific remote. So if you've got something that is changing or dynamically changing multiple times, we have to have the ability to essentially flush that information out of the system. To do that, we've actually just based it upon a time. Most of those time, this really came up when we had used these radios in a public safety event for police, and they were finding that if they did not update that time after each shift, then what would happen is that that radio would think it's talking to a different piece of hardware, a different computer that another officer had. Well, so what we did is we just set it at a specific time. So every 8 hours, at the end of an 8-hour shift, it would automatically flush those out, re-find what the ARP time is, and put it back in there again. You can even set the time to where it never updates. So the only time that you'd ever have to update that dynamic ARP list is say you put in a new piece of hardware out at a remote site, something like this. The next thing is that most of the way that we handle multicast traffic within the Horizon, and quite honestly, most of the other radios that we put out there, is we're not actually sending it out as a multicast packet. What we're doing is we're taking that multicast packet and rebroadcasting it as unicast packets. The only reason that that's important is that if you have multiple remote sites as you're sending it to, say we're connected to 10 different remotes, instead of taking that multicast and sending it 10 times, now we have the ability with this multicast option to truly send it as a multicast packet. So it'll send it out one time. If the remotes hear it, they'll do it. The last thing that we've added to that, especially this first generation firmware that optimized this network, was what we call a whitelist. The whitelist is another way of doing kind of a router mode. But what we do it is you put a list of IP addresses, and that radio will only process or send traffic for those remote devices. It can be a little more complicated to do that because you'd have to update it. And the best part is it only sends those ARPs for those addresses in the whitelist. So you are effectively getting the same function that you got out of a router, except it does not block all the traffic for that like a normal router would. That's really where we came up with this second generation of firmware. This second generation of firmware allowed us to do a true router mode. It limits the over-air traffic to the IP range, and the biggest traffic reduction that we get is no beacons are required. The only traffic that goes across there is when the Ethernet device itself sends information. We're not sending communication between the radios to keep the link operating. We also support the bridge mode, much in the same way we did in the first generation. The difference is that we have the ability to actually turn the beacons off. So you can actually put them into a bridge functionality, turn the beacons off, it will open up tremendous amount to it without having to put in all the router information. The difficult part is because of the functionality and the over-air transactions between the two, there is no compatibility between the first generation of firmware and the second generation of firmware. So if there's any question as far as which of the type of firmware you should be using for your application or the best one to operate on, the best thing to do is call into support. So let's take a look real quick at the 210 as far as the configuration of it. We'll see what each of these type of methods actually do. So what I'm going to do is I'm going to open up here on the screen. I'm going to bring over the Discover utility. I'm going to hit the Discover button. And what we're going to see here is we actually have a model 210M connected that is running the IP address 172.16.58.162. That falls within our Class B range. So to program this radio, we simply click on that line, do a right mouse click, and hit Configure Radio. All right. Now on the web browser, we're going to sign into it just like we did with the Horizons. We're going to use the same username and password. By default is admin, A-D-M-I-N, for both the username and password. We'll enter those both in here. And what you're going to see is you're going to see a configuration window that is almost identical to what we had on the Horizon series. There are a few different parameters that you'll see that's a little bit different. A little bit of the menuing is a little bit different. You'll see on here that we don't have a wireless status. There are just things in different areas. So the configuration of this radio the best way to go through it, and depending upon the generation, we do have within the user's manual and a technical bulletin for each one of those. But generally, most everything is done here in the setup page. So if I click the setup page, this one here is actually a first generation first firmware. So as you can see here, we actually have the AP bridge, a station bridge. The earlier one had what was called an air scope mode, which allowed you to turn the radio into really a wireless sniffer, is what it allowed it to do, to show the packets going back and forth. The next thing is this mode also supports Ethernet only. So let's say, for example, we're going to program this as an AP bridge side. We're going to make this the bridge side. So we select AP bridge and hit the next button. Now, the first thing it's going to do is it's going to come up and ask us as far as what do we want to do for the IP side of it. So for this radio, what we're going to do is it's going to ask us for the IP address. So this one here, we started out, we just had it at 162. There's our net mask. The IP routing, being a bridge side, doesn't really matter which route we put in here. And these are the different QAM modulations available to us. The difference as far as speed goes, you'll see actually happens here, depends upon the channel width we have available. By default, every channel that's the FCC license right now is 12.5 kilohertz. They also put out a warning that not too far into the future, both the VHF band in the 150 to 174 and the UHF in the 450 to 470 will lower to 6.25 kilohertz. So we've put that in as an option. And as you can see, the bandwidth that you select and the QAM modulation directly affects the actual throughput. Most application where we've put this, 64.8 kilobits per second or 64 QAM works very, very well unless you get into an area that has a tremendous amount of reflected signals, noise, or if you you're going through trees or vegetation. In most of those cases, then those will then operate at 43.2. We've never run across a case to where you actually had to drop all the way to 61.6, although that is a possibility in an incredibly noisy environment. So most of the time you're dealing with 64.8 or 43.2. Then we just simply add or put in the frequency of operation on this last line here. I'm going to leave this at 64.8, and we hit the next button. As you can see, we don't have as many different possible configuration choices as we had in the Horizon series, but many of these that we have up here are very similar. For example, if we have the SSID, well, instead of having it as a name field to where you'd put any kind of an alphanumeric characters in there, we've just simplified this to it's a number anywhere between 0 to 255. So every radio that is going to communicate with each other needs to be on the same SSID number. We also let you choose which level of encryption do you want to run. Do you want to run none? And again, keep in mind these are a proprietary type of communication. So even running no type of security does not mean that you can easily sniff what type of communication is going across there. You'd have to have very sophisticated device even to interpret what that data is with no encryption. Each one of these encryption methods that you put on here adds more and more overhead to it. So if we get us all the way up to CCMP, which is our highest level of encryption, it's nowhere near a percentage of how much it's going to take off. In other words, the most we generally will lose from the no encryption all the way to the highest level of encryption is about 10% of throughput. So it's not a massive amount of difference between the two. It just really comes down to what the application requirements are for the system it's going into. So if we're going to set it at none, we make sure our SSID is going to be the same. We'll go ahead and hit the next button. So where this is going to take us now is it's going to take us into the network optimization menu, as I mentioned to you before. Do you want to enable the dynamic ARP proxy? What timeout do you want it to go? So if it's actually set at 0, then that means that time will never flush. It'll hold it forever. If you want to do it for every minute, you'd set it for 60 seconds. The next thing is the net filter multicast. So if you want it to be handled as a unicast packet, then you could set it to no. Most cases, you'll just leave it to yes. And then you have the ability to set the whitelist. Now, the thing to keep in mind on the whitelist is that you have to put in all IP addresses that radio would deal with. For example, if you come out to a 210 network that has the whitelist configured, and the computer that you're connecting to it, its address is not in the whitelist of the connecting computer, it actually won't talk. So what we've done is we've actually recognized that that is a possibility. I'm going to flip us back over here really quickly into the Discover utility. Bear with me for 1 second. I'll bring it back up here. I'm going to share the Discover utility because there is one feature that we've added in here on the 210 network. Recognize that we can run into a problem there. If you do a right mouse click, go down to the advanced, you can actually easily just whitelist the IP address of the radio you're connecting into that device so that it won't immediately kick you out if it's not part of there. Again, this is a temporary whitelist. As soon as that radio is reset, that IP address is pulled back out of there. So it is a temporary, but it is a way to get in there if that is actually set. So let me go back here to our web configuration page. The next thing it's going to ask us is which peers are we going to communicate to? And again, much like in the way that we set the horizon, the only question it's going to ask us now is that we've consolidated this page to handle both the root bridge and whether or not you're going to be running the spanning tree. In other words, are the links going to be changing? So when we add information, it needs to know the serial number of the remote we're talking to or the wireless MAC address to it. The path length is exactly the same way that we went through and we did meshing on the Horizon series. And we then need to identify what kind of traffic is going to go across or be limited. So the way it's listed here is very simple. If you're going to be sending out Ethernet transactions, you leave it in multicast. If it's going to be doing serial communication across that link, it needs to be put into a unicast. We also need to know if it's going to be fixed or it's going to be a mesh. It just depends upon how often we update the status packets going between the radios themselves. This enable and disable, you actually have the ability, you could put all of the remote sites in there and then just only enable those that are going to be active. It was a way that we used early on, a method of programming or quickly programming all the radios. It's kind of a legacy really into what we're doing now. So what I'm going to do is just return to the peer setup here. I'm going to go ahead and I'll just set these back at no because I don't have another 210 connected here that I can link up to. You'll see here now that this next to last page is the RS-232 setup that we saw in the Horizon series. That was an option that we turned on or off. This one here is always active. So what we do is we set the baud rate parity, maximum number of hops, the multicast traffic, and the single remote is exactly the same the way that we did it before for the Horizon series. This last and final page allows us to essentially commit the changes here, but we also, if you wanted to give that radio a name, what you would do here is instead of committing the changes here, you just simply hit go to the advanced setup, go to the global variables, and under the global variables, just like it is on the Horizon, the modem ID is listed here. So we could call this the remote. Okay? So the nice part is that if you are going to change the name of the radio, the best thing to do is instead of committing the changes, jump to the remote and then make the changes and then finally hit the button that says commit and reboot to get the radio in operation. Now, this 210 can be put into multiple modes as we see here. The best thing to do is if you've got an application that is going to be utilizing this type of radio, that the best thing to do is give us a call. We want to walk you through what the capabilities of this radio are actually going to be to make sure that we don't you don't put the radio into a situation to where it's going to use too much bandwidth. We're not going to be able to support the type of environment you get into. So we want you to be successful with this more than anything else. So we want to make sure it's not being put into an application where it's not immediately going to work. So if you are looking at the 210 series, that is something that we'll probably want to discuss the type of network that you're putting it into. So we put you in the right mode, the right generation of firmware, everything like this. All right. So that covers everything that we need here on the 210. The next thing that we're going to go into, the next radio, is we're going to take a look at all of these programming applications that we've utilized throughout this training class. We're going to look at each one of those in greater detail. So thank you very much and have a great day.